Ideal gas law, pressure versus volume, and volume versus moles. Hold the temperature and number of moles constant and find the relationship between pressure and volume. Solve for P and then combine all the constants together in parentheses. So here's PV equals nRT. Divide both sides of that by V, and you have P is 1 over V times nRT. This shows that with N and T held constant, and of course R is a constant, P and V are inversely proportional to one another multiplied by the constant nRT. Solving for the volume yields the same 1 over X relationship. Right? This time we have volume is 1 over P times nRT, and up there we have P is 1 over V times nRT. Rather than a linear relationship, this is a Y equals 1 over X relationship, and this is just a constant here. The curves would have the same shape if we reversed the pressure and volume axes. Right? If we put the pressure on the x-axis and the volume on the y-axis, but typically you put pressure on the y-axis right over here. It's a pressure-volume graph. The curves reflect the same 1 over x relationship, but with different values of the constant nRT. The blue and red lines reflect the relationship between P and V for the same amount of gas at different temperatures. Since the 1 over x curves are multiplied by the constant nRT, the higher curve, the blue line, has a higher temperature. This one right here, higher temperature. As the volume of a container increases, with a constant T and number of moles, gas particles collide less often with the container walls, resulting in a drop in pressure. So here we have a volume of 2 liters, more collisions, higher pressure, 32 millimeters of mercury. Over here, fewer collisions, lower pressure, and a pressure of 16 millimeters of mercury. The inverse relationship between pressure and volume is known as Boyle's law. A linear plot can be obtained by plotting V versus 1 over P or P versus 1 over V. In either case, the slope will be nRT. So here's a volume versus pressure measurement, and that would be this one right here. Right? The first one is typically your y-axis, so that's volume. And the slope of that line will be nRT. And look what we're plotting down here, 1 over P. This way we turn that curved line into a straight line. Soaring birds like the California condor rely on hot air rising in order to stay airborne for long periods of time without using much energy. Explain why hot air rises using the relationship between volume and temperature, Charles's law, and the concept of density. As the sun warms the earth, the temperature of the air increases, increasing its volume, that's Charles's law, and decreasing its density compared to the air around it. The hot, lower density air rises. Note, these updrafts are not everywhere. They are often broken up by cooler air returning to the surface. So the condors have to be careful. Hold the pressure and temperature constant and find the relationship between volume and the number of moles of gas, N. This is like inflating a balloon. Solve for V and then combine all the constants together in parentheses. So we have our equation here, the ideal gas equation. Divide both sides by V, and here's our constants right over here. This shows that with T and P held constant, V is proportional to N, and the proportionality constant is RT over P. As the amount of gas changes, the volume will change proportionately, and vice versa. Once again, we'll compare with the equation of a line, and here's our V as a function of T, P, and N. We see we have a slope of RT over P, that's inside the parentheses, and a y-intercept of 0. Remember once again, R is always constant, and that T and P are constant for this example. The y-intercept shows 0 temperature and pressure when there is no gas. So, whenever T and P, temperature and pressure, are held constant, the graph of volume versus number of moles, here's volume, here's number of moles of the gas, will be a straight line. For different samples of gas, the slope may differ depending on the fixed values of T and P for that sample. These two lines have different slopes due to differing values of RT over P, right? Because that's the slope. The volume of a gas at constant temperature and pressure is directly proportional to the number of moles of gas. The more particles that there are present, the more room they will need to move around if the pressure is to stay the same. So here we have 2 liters with 4 moles, and here we double the volume to 4 liter, and that doubles the amount of moles. So the direct relationship between the volume of a gas and the moles, parentheses little n, of a gas is called Avogadro's law. This chart shows what we're allowing to vary, what's held constant, the relationship between the variables, then the relationship between the variables, where k differs in each case, and then a graph. So P and V are varying, T and N is constant, you have an inverse relationship, and PV equals K. And the graph looks like this guy over here, 1 over X graph. And we'll let you look at the other 3 lines and notice that the graphs for each of those are straight lines. So if you want to study this or write it down, please pause the video and move on when you're ready.